Hello everyone, this is Doug here, and in this video we're going to talk about the Sonogashira reaction, which is another powerful palladium-catalyzed cross-coupling reaction. So remember before, right, we said that in this class in organic, we're just going to look at 3 organometallic reactions where you talked about looking at the Suzuki, which is this path right here. We are going to look at Sonogashira, which is in this video, which is this path right here. And then in another video, right, we're going to look at the Grubbs catalyst and metathesis, which will be that one. So watch for that next. So what is the Sonogashira reaction? Like I said, it is a palladium catalyzed cross-coupling, so you're definitely going to see palladium. And it's similar to the Suzuki reaction in that you have to start with a molecule that has a good leaving group on it, right? So here's that leaving group again. And just like before, it can be things from like chlorine, bromine, iodine. It can be things like tosylates and triflates. And what you're going to see is that this carbon, again, like Suzuki, is usually going to be sp2 hybridized. And it could be sp hybridized. And there's new methods to make them sp3, but still, just in general, it's going to be sp2. I'm mostly going to be showing you those. They're the most common types of coupling partners that you're going to see. The way that this differs from Suzuki is that you're always going to couple it to a terminal alkyne. So not a boronic acid or boronic ester. It's going to be a terminal alkyne, right? So that just means an alkyne at the end of a chain. So at end of the chain, right? Like we have down here. Here's our terminal alkyne. Right, it's got a CH here. It's important that you have that CH because that's the part where it's going to couple. And then we're going to have our palladium, which is not a surprise, given this is a palladium catalyzed cross-coupling. And it'll be the same thing. Usually we add them as palladium-2 salts, and they become palladium-0 at some point during the catalytic cycle that I don't care that you know. One way that they are different than Suzuki's is that you also have to add copper 1 salts. So it has to be copper plus 1, not copper 2, copper 1. And you almost always see that as copper 1 iodide. It doesn't have to be copper 1 iodide, but just copper 1, copper plus 1 somewhere. Now let me write out that name here. So this is copper 1 iodide, right? Because it's got a plus 1 charge on it. And again, don't worry about the mechanism, just we need to have the copper in it for reasons. And then lastly here, you're going to need to have a base also, which is similar to Suzuki. One difference with Sonogashira here is that this base is often an amine. So I'll put often an amine. So you're going to see bases, like TEA, which we know, or we should be very familiar with triethylamine. Or you'll see things like DIPA, 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 which stands for diisopropylamine. Things like that. So oftentimes you'll see these amines. You can use like carbonates and stuff, but oftentimes the amines seem to work really well for these, and so you're going to see a lot of those. Now, if I compare that to the example that I have down here, well, actually, let me stop. So if you take a look here at this just generic thing, right? So the idea is that we're taking whatever was connected to that leaving group, so this aromatic ring, and we're going to connect it to whatever that terminal alkyne was. So wherever that H was, that's going to be gone, and it's now going to be attached to where the leaving group was on your other molecule. Right, so you just attach the two together, boom, leaving group is gone and H is gone. They're now coupled together. You've made a new carbon-carbon bond there, right at the point of attachment for that alkyne. Now, if I look at this example down here, this is a good example of a Sonogashira, right? So we've got a sp2 carbon, check. It's got a bromine on it, check. So I know that this piece right here, or sorry, this whole piece with the methyl, is this piece, right? So I'm going to take that whole piece and I'm going to connect it to, right? We've got our terminal alkyne, right? You don't see the CH there, but there is an H there, right? Which is why you attach it to that point right there. So you literally just took those 2 big carbon pieces and put them together. And then yes, we see some palladium. Yes, we see some copper iodide. And yes, we see our base. In this case, it was the triethylamine, the TEA. And again, these reactions are fairly high yielding. They're fairly quick. and they're very reliable and don't mess with a lot of other functional groups. They're very functional group tolerant. Let me show you another example. So if we look at this one, right, still Sonogashira, this is a little bit different. If you take a look at this, right, yes, this carbon is still sp2, so that's perfect. Here we have the tosylate, which is a good leaving group, right, like bromine and iodine and stuff like that. And like the Suzuki reaction, whatever stereochemistry you have here, you keep. So we're going to keep the stereochemistry. Keep the stereochemistry around that alkene. Right, it doesn't get scrambled up. So in this case, let's see if we do this right. This is the Z, right, because you have the highest priority groups on the same side. So if this alkene is Z here, it needs to stay Z here, right? If it was cis, stay cis. If it was trans, stay trans. You just need to maintain that orientation because it doesn't mix things up. And so wherever that leaving group was, right, so here's my molecule. I'm just going to take wherever that leaving group was, that's where I'm going to put my alkyne. So here's that group. Leaving group was right there. Slap the alkyne on there. Boom, you've got a new carbon-carbon bond and a more complex molecule, just like that. And again, in this example, they use copper iodide and DIPA. So those are two good examples of the Sonogashira. You just got to find where that leaving group is, find where that terminal alkyne is, and you put the two together right there. That's all there is to it. So let's look at some examples. Again, this would be a good place for you to go ahead and pause, see what you can do with these. Look at the notes we just had, right? You just need to find where the leaving group is. You need to find where the terminal alkyne is. You need to put the pieces together. And one of these asks you to come up with the reagents, so you can figure out what those are. Again, they're pretty predictable if you know what's supposed to go into a Sonogashira. And then we'll do a synthesis after this. So go ahead and hit pause here. I'll stop talking for a sec so you can think. Okie doke. So hopefully you had a chance to think. I put this one up here. Maybe I shouldn't have started with this one, but I think it's good anyways. In this one, you have an iodide and a bromide, right? So you have a iodide, so I'll say iodine since it's not negative, and you have bromine, right? So you have iodine and bromine. They're both leading groups, but generally speaking, for us, for now, you just assume that the better leaving group is going to be the one that leaves. So since iodine is a better leaving group than bromine because it's more stable when it comes off, right? We're going to cut at the iodine. And this is just one equivalent, so I'm going to replace just one of those, not both of those. Now, you can kind of ignore what I'm about to say because this is not organometallics class, but what's really cool about organometallics is that by changing the ligands on the palladium and the type of base and stuff like that, you can often tweak the reactivity so that you could make this exact alkyne actually go to the bromine instead of the iodine if you wanted. There's just all these little tricks and stuff that you can do with these organometallic reactions which make them so cool and so interesting. But for us, for organic chemistry, whichever one's the better leaving group, switch that one out. So I'm going to take that whole thing I squared off in blue, and I'm going to take my alkyne here, right? There's my terminal alkyne. TMS just stands for trimethylsilyl. It's a protecting group. It has a silicate. Well, let me write it out for you, since you might want to know. TMS is a trimethylsilyl. So here's the silane, and then you have a methyl group. Let me draw this out a little more space. It's a silicon atom with a methyl, and a methyl. Right, that's what TMS is. So then you'd be attached. So that's saying that this molecule right here is that. Right, so that little bit is TMS, trimethylsilyl. Who cares what it is, though? I know that I just slap that on to where the iodine is. Right, so when I go to draw my molecule, I'm going to draw this fused aromatic ring thing. I still have a bromine here, but now I know that I'm attached to an alkyne that is attached to TMS. And so that's what I'd write for my product. Right? Just put it on there, make that new carbon-carbon bond, and you're done. For the second one here, it looks like now I definitely have, so here's my thing with the leaving group. And if I look to my product, I see that over here, I see that furan thing, and then I see that I have my terminal alkyne that looks like that. So I just know that that's what my terminal alkyne looks like, right? It's this isopropyl thing on an alkyne, so that's the piece. And then I need to add all the other stuff that I need. And I can just look at the one above it, but you know that you're gonna need palladium with some sort of ligands and stuff, some copper iodide, and then you can pick your favorite base. I'll do, let's do DIPA since it's not on here. All right, the top one was triethylamine. Let's put DIPA for this one just for fun. You could put triethylamine, it doesn't matter. But those would be the reagents, right? Copper and palladium and an amine base. That's what you're looking for. Here's a cool example of some sugar chemistry here. Someone's trying to make something interesting with the sugar. Don't really care what it's used for. I'm sure it's fascinating. But for us, for the Sonogashira, right, I just know that I need to attach these two things together. So I'm going to draw this crazy sugar and do the best that I can to not lose carbons or anything. I'm not going to change any stereochemistry of any molecules. Oh, that was actually a wedge, so let's make that a wedge. And with the acetate group there, acetate group here, double bond, and again, you keep the stereochemistry around the alkene, right? That's why I wanted to put this one on here. If it says that it's moving up like that, keep it up. And then you have the alkyne, and then apparently this like decyl group. So C10H21. You don't need to draw out the 10 carbons. You could if you wanted to, but whatever. That would be your product. All right, so I just replaced where that bromine was with that alkyne, and I'm done. And lastly, this one's kind of cool because you notice that you have 2 leaving groups. You've got an iodine, and you have 2 equivalents of this alkyne. And there's no reason, right? If you have lots of alkyne and you have lots of leaving groups, they can all react. And so this sucker is actually going to put 2 on, which is pretty cool. And this is actually like a lot of chemistry that used to be done at the U of O with Mike Haley's group, where they would make really complicated aromatic rings that had alkynes in between them. I'm going to draw this O-methyl. And to make these really big, interesting frameworks and pincer molecules and stuff like that. And O-methyl. Right, so I just put that alkyne, right, this alkyne right here, is these 2 pieces. And then that center piece with the 2 iodines is this piece. So I just slap the 2 together. That's all you have to do. Very straightforward as far as figuring out what the products are. You just got to remember that Sonogashira is the one with the alkynes and the copper. So how about some synthesis stuff? Like what might you use this for? Why is this even important? We've seen alkynes before. We know how to make alkynes. If you consider for a moment trying to make this, and if you want to challenge yourself, go ahead and pause and see if you can make this not using the Sonogashira. Do not use the Sonogashira, and see how many steps it takes you. It's gonna take a lot. So like if I was to look at this, man, I mean, this is going to be a lot of steps, right? So I'm starting with the anisole. Let's say we start with the Friedel-Crafts. And let's use the anhydride this time and maybe something like phosphoric acid. So that I can phosphorylate, right? And it's going to be, I'm going to get ortho and para, but probably a lot of para. I'll have to isolate this para. And I need some way to get, I need to get some more carbons over here. But I can't do another Friedel-Crafts because I'm starting to, well, you know, this is kind of borderline. I'm starting to deactivate it by putting the acyl group on there, but I still have a strong activator because I have the OCH3. But I'm just going to cover my bases here. I'm going to cover my bases and protect that carbonyl, just to be sure. And even this is kind of a sketchy step, but well, let's just go with it. So I protected my carbonyl. So now if I wanted to do, let's say I want to add 1, 2, so I want to add 1, 2 carbons. So 1, 2, and then a phenyl ring. Let's say AlCl3. To then put on that other group. But see, even this, I don't even know if that acetal is going to hang out when you add aluminum trichloride because it's such a strong Lewis acid, but let's pretend for this reaction that it does, although it probably doesn't. I can imagine getting to here and then saying, okay, well, let's use like NaBH3 or LAH or something like that to reduce that carbonyl. That ring got too bad. I'm getting to the corner, so I'm getting lazy. Let's be good. Here we go. Much better. And now I have an alcohol, and I'm just going to put a phenyl here at that pH for the phenyl. What I could do now is try to do a twofer here. No, I think what I'm going to do is I'm going to go ahead and use SOCl2. What I'm going to do is I'm going to try to do an E2 reaction. So I'm going to do step 1, SOCl2, step 2, something like LDA or even sodium hydroxide would be fine, and we don't have any regioselectivity here. So I can make an alkene there, right? So I can make this. And I'm almost to an alkyne, right? I know I can take my alkene. Well, I'll just save myself some steps. If I want to turn this into the alkyne, I can do step 1, add something like Br2 to add 2 bromine, so I have that geminal dibromide. And then step 2, right, add NaNH2 to get the alkyne, right? I need at least 2 equivalents to make that alkyne. Oh, and then I forgot that I should do a step 3, which is just an acid workup, so I can get rid of my acetal and bring my carbonyl back. But still, that's a lot of steps. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, like 9 steps. It's a lot of steps. It's a lot of work, a lot of time, a lot of waste. Nobody wants to do that. Plus, like I said, there's some kind of shady steps in here that I glossed over, but still, it takes a lot. We can't just Friedel Crafts an alkyne on. It doesn't work like that. You can't just like put a chlorine at the end of that and then attach it. That's not a real thing. That's not a reaction. Nor can I just put, nor can I put this whole 2 carbons plus the phenyl group thing on there using Friedel-Crafts alkylation, because it's probably going to rearrange, especially because the benzyl position is so stable. So this is probably the best that we got at this point with what you've learned in OChem so far without palladium catalyzed cross couplings. But with a palladium catalyzed cross coupling, this is a lot easier, right? Because I can do the same first step. Whoops, just kidding. I can do the same first step here, where I'm going to go ahead and do the acylation, Friedel-Crafts acylation. I'll add my phosphoric acid and the acetic anhydride. Got my OCH3. Got my acyl group attached here now. I could go ahead now and just do like a bromination or an iodination. So let's just do Br2 and FeBr3. I just need some leaving group on there. And again, if you look at your directors, right, this is a meta director, this is an orthopara director. Either way, they're directing to these positions. So that's going to be perfect. That's where I want the bromine anyways. And that's why I put the acyl group on first too, by the way. So OCH3, put a bromine there, and then boom, I already got a bromine on there. I'm just going to Sonogashira this sucker to get that whole piece on there. So I know that the alkyne that I want is just this alkyne with this aromatic ring. Boom, and then if I want to do Sonogashira, I know I need palladium with a couple ligands. I know I'm going to need a amine base, so let's just go with triethylamine because that's easy for us to remember. And I know that I need that copper iodide as a salt. There we go, Sonogashira. So I could do that, whatever I said, 11, 12 steps, something ridiculous, or 3. And this is way faster, way more efficient, better yields, less waste, much greener, etc., etc., etc. So hopefully you can appreciate that the Sonogashira reaction is also a huge time saver and really important and widely used. So do some practice. Let me know if you have any questions, and happy studying.